welcome to day 7. Today is the first full week of doing videos.
Yeah! Yeah! Yeah!
I forgive you.
And today we're just going to do an educational video.
Boo, Indy, boo! Boo, Indy.
We're going to go lesson 1. We're doing geology.
Here I am, trying to make it right. Gonna take my life back with my baby tonight.
This is for water well drilling. Let's see. Geology, it is the study of rocks and earth materials. Given the worldwide deployment capabilities of a water well team, the basic understanding of geologic principles is necessary. The geology of an area is the underlying factor for decisions made in well drilling and is an important component for understanding how the drilling operation will affect the environment long after the conclusion of the project.
Wow, look at this. Do you know what this means?
Right. So practically every decision made in drilling, from the site selection, soil, water, minerals, to the specific tools used to make the hole, is based on geologic conditions. Right? It's all about what you're drilling into.
Oh, I apologize for the double entendre. I can be such a Samantha.
It's all about the formations. The geologic conditions usually can determine the well drilling method, whether it's going to be air, mud, rotary, or hammer. Right? Geology is the study of rocks and earth materials. Understanding exactly what the well recipient needs is crucial.
I need you to hook me up.
What do you need? Synthetic veal, porno, mint jelly?
All of them, if you can.
The amount of water bearing potential is dictated by the geology of the area. Knowing the amount of water needed by the customer will validate the viability of the well. Right? Can the customer realistically expect a certain potential with the type of geology in that area? Like if you're in a mostly rock area, there's not going to be a lot of water bearing potential in that area when you're drilling for water, right? Knowing the amount of water needed by the customer will validate the viability of the well. Right? It is impossible.
It is impossible
To actually see the bit working. Indicators must be used to make adjustments. Right? You can't see what's happening inside the hole. You have to use context clues to figure out what's going on. Right? A good understanding of geology helps visualize what's going on in the hole. If you know how the geology in the area usually is, you can usually figure out what you're trying to drill through.
Come in close. Closer. Because the more you think you see, the easier it'll be to fool you.
Right? Using context clues on the surface to figure out what's going on inside the hole. This is something we can cover in later topics. Right? Certain materials break differently. Right? A drinking glass breaks into sharp pieces, and a windshield or tempered glass shatters into hundreds of small pieces. Right? Crushing or hammering will not break up a motor tire. Slicing action is required. Geologic formations also break in different ways. Selecting the wrong bit will result in no penetration or very slow drilling of a hole. Shert breaks into sharp flakes, requiring a bit that gives it a sharp knock. Sandstone crumbles or tears apart from the grain to grain, requiring a crushing or tearing action. Clay is soft and does not react to crushing or hammering. It requires shearing and clearing. Right? The earth consists of layers or zones known as the crust, mantle, and core. Drillers are only concerned with the crust. Modern drilling capabilities fall significantly short of reaching the mantle and core. There was a hole that was drilled in Russia. It was a pilot hole, about like 6 inches in diameter, about that big. and it went farther than anyone has ever drilled before, and that was only maybe a mile down.
The Kola Super Deep Borehole. Ooh. Its depth is 7.4 miles. You can find it in the icy part of Russia.
Don't quote me on that. I'll throw something up to visualize that one. Clay. Yep. We talked about clay. Right. The crust is divided into giant plates according to the theory of plate tectonics. Continental drift and seafloor spreading are the best known features of crust movement. As the Americas, Europe, and Africa pull apart, the Atlantic Ocean increases in size.
The Earth is dynamic, constantly changing, and its land masses have been shifting and colliding over millions of years, and have so far left us with the 7 continents we see today.
As the Atlantic Ocean increases in size, obviously the Pacific Ocean decreases. That's just how it works, man. The continental drift and seafloor spreading are the best known features of crustal movement. As the Americas, Europe, and Africa pull apart, the Atlantic Ocean increases in size. I read that one already. Slow tectonic movement is the background for all geologic activity. As it is presently understood, mountain building results from crustal pressures. They press together and push up, and you get mountains.
Belts are created when continents collide. In this experiment, we see 2 continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt. The green sand represents the rocks of the ocean basin. Note that it's been trapped between the 2 continents, marking their original boundary. These too we see in mountain belts.
Another result of tectonics is the recycling of rock. The only visible part of the mantle comes up in the form of hot molten rock known as magma. Volcanic basaltic magma, dark, very hot, and fine-grained when cooled, comes from the upper mantle and flows out through mid-ocean volcanoes. For example, Hawaii, or any of those other islands on the volcanic ring.
Huge arc of geological destruction surrounding the Pacific. It is known as the Ring of Fire. 3/4 of Earth's volcanoes are situated here, and 90% of all earthquakes also occur along this line.
Ring of Fire, as they say. Plutonic or granitic magma, light in color, more viscous and cooler, coarse and grained when cooled. Magma is produced when solid parts of the crust are melted due to increased temperatures. Right? Rocks are aggregates of minerals. Right? It's important to know that rocks are aggregates of minerals.
Do me a favor, keep that kind of shit to yourself.
Usually in the form of interlocking crystals or grains bound together by natural cement. Knowing and understanding the different types of rocks is a very useful skill and beneficial in planning a well drilling operation. Rock can be made of many minerals. For example, granite contains quartz, mica, feldspar, and
Granite is some of my favourite rocks. They make up a large part of the Earth's continental crust too.
Hornblende, or can consist of one mineral. For example, limestone is composed of the mineral calcite, calcium. Right?
Limestone, to make it simple terms, is a sedimentary rock. All limestones are calcium carbonate. They are fossilized shells, bones. Just because it's a limestone doesn't mean it's soft.
Rocks are classified into three main groups: igneous, sedimentary, and metamorphic. This is important. Igneous rocks are formed by the solidification, cooling, and crystallization process of a liquid rock material known as magma, right? Rocks that solidify at considerable depths in the earth are called plutonic. Plutonic rocks, such as granite, range in colors of white, gray, pink, orange, or green. The texture of these rocks is classified as medium to coarse-grained. They are generally low water-yielding formations, and water can occasionally be located in crevices and fractures of upper weathered zones. Right, so whenever you're drilling into hard rock, you're looking for fractures within the rock that hold the water, right? Because the rock itself can't hold water. See what I'm saying? Rocks that solidify at or near the Earth's surface are called volcanic. Volcanic rocks, such as basalts, are reddish-brown in color. Due to rapid cooling, they usually have a fire-grained texture and a glassy appearance. These rocks often contain interconnected openings and fractures which provide space for water. Sedimentary rocks are the deposits of minerals derived from the weathering and erosion of other rocks. They make up only about 5% of the Earth's crust, but contain an estimated 95% of the Earth's groundwater. These rocks can be consolidated or unconsolidated. The consolidated, often found in easily recognizable layers, known as sedimentary rocks, right? Red Rock Canyon, for example. Limestone, calcium carbonic, a precipitated rock that contains fractures and crevices. The flow of groundwater through interconnected openings forms solution channels, right? This is important. Sandstone is formed by the compaction of sand, right? As the sand's compacted, it cements and creates sandstone. The water-yielding capability of a sandstone formation varies with the degree of cementation and fracturing. Right? Shale, compacted, and cemented clays such as mudstone and siltstone are known to yield small amounts of water in areas where the earth movements have substantially fractured the formations. Right? So, in the interest of time, and because I'm still new at this, it takes me a long time to edit these. Well, we're going to end that today. Tomorrow we will have part 2. Cool. Thank you very much.